K8BYP with the fourth video in the Tuning and Matching Network series on actually doing some calculations. But first, I hope you're enjoying the video short from DC Cab with a flamethrower. I thought that was really cool. That's a movie, DC Cab, from the 1980s. If you're going to do it right. Here's a page from Kurt Blankenbush's RF Cafe site that gives convenient formulas for impedance, phase angle, and admittance for various circuit components and configurations. I've derived some of these formulas. The ones I've derived are accurate, so these should be reliable. In the process of developing my HF power amplifier, I'm looking at using fixed values for an output network. Saves a lot of money. And here's an assumption of what if that I did using formulas in a Radio Engineer's Handbook of two 150 puffs in series and a 12.8 in shunt. And that has the advantage of blocking DC with the inductor being a shunt. That eliminates, if this will work, that will eliminate two components. Firstly, a blocking capacitor, and secondly, a DC shunt choke that's usually at the output. So the process for doing this calculation is to take this branch, the 150 puff and the R50, as a impedance in series, find the reactance of the 150 puff at 3.7 megahertz, which is R50 minus X287. That'll be converted to an admittance. The inductor, Z sub L, is 12.8 microhenry. That is R0 plus X298. Right away we notice that this inductor and capacitor pair are close to resonance. And that's one of the conditions of this transform. Take those impedance forms, invert them by drawing a divisor line over and putting a 1. And then, take these forms and put them into a magic formula, which is essentially doing that. And out comes two admittance values. That converts these impedances to admittances, add the admittances and convert it back. And that gives the impedance at this node. That needs to be an impedance because this node will be in series with the capacitor here, which also implies in series with a source resistor here. So here we have Z sub 1, the R50 minus X287, which is the so-called right branch. And we put that in our magic formula. And the magic formula simply takes the impedance, change the sign, and write it in the numerator. Nothing else. That change of sign implies what I mentioned in an earlier video, that when in series, the capacitor reactance is minus, but when in shunt, it's plus. And that's exactly what that plus sign means. Down below, take the coefficients, 50 and 287, square them, and always add them. And the J operator is hiding behind that plus sign. It's always plus. So simple, I can't even mess it up, but I do anyway. What's really happening to arrive at this is inverting this impedance to get an admittance and multiplying through by a unity fraction when making this plus. And that's what ends up being in this form. There's no point in doing that. Add the denominator, and out comes R50 plus X287 over 84,869, which is Y sub 1. For Z sub 2, the inductor by itself, it's R0. There's no resistance in series with the inductor. Plus X298, calculated from finding the inductive reactance. Numerator, R0 changes sign minus X298, making it capacitive, over X298 squared. Remember, these X's are not variables, neither is the R. They're just there for housekeeping, to make this clear. I use this as a substitute for chasing the J operator around. This is much easier. And under the rules for adding impedances, this keeps clear which is which. In adding two impedances, we add the R value and the X value. That equals R sub 0 minus X298 over 88804. That's Y2. We can't add those because they're fractions with a different denominator. So we have to take the larger denominator over the smaller and get a correction number, take that as a unity fraction and multiply that by this to raise this denominator to be the same value of that, which will also increase the value here. Then those two fractions can be added. Both fractions must be the same denominator. 88804 over 84869 equals R50 plus X287 over 84869 times the unity fraction 1.046 over 1.046. And remember, a unity fraction does not change the value of that. It's scaling the numerator and denominators up by the same amount, so it doesn't actually change the value. That equals 52.3 ohms plus X 300 ohms over 88804. And I cheated here because it doesn't come out exactly 88804. It comes out a little different. It comes out 889 something, but it's close enough. So there's an error there. I want better accuracy, use more decimal places from that fraction. So now they're the same denominator. We can write that as a combination of these two impedance values up here. And from adding impedances, we add the R values together. We add the X values together, noting the signs are opposite. So we get R52.3 plus X2. R52.3 here plus X300 minus X298 is plus 2 over 88804. That's the total admittance at this point. That can't be put in series with, that's here. It can't be put in series with that because it's in admittance form. So it's got to be converted back to impedance to be put in series with that. There's the admittance. To go back to the impedance form, we note that admittance is the inverse of impedance. So we flip that fraction over. We get 88804 over R52.3 plus X2. This form has to be in the numerator, so we multiply through by this with the sign changed again with our magic formula, and I'm showing it here. Note the sign change. So I've actually expanded and shown that step here. But it's still this process. Where did it go? It's still just this formula. Take the impedance form, change the sign, put it over the squares of the coefficients. So that becomes, and here's where it's important to keep it in this next form. Don't try to do all the math. 88804 times in the numerator R52.3 minus X2. Don't multiply that through. That causes a mess. Leave it in that form. Over the product of the coefficients in the denominator. 52.3 times 2 is 2739. And at this point, this number should be larger than that. Divide that number into this and get a coefficient, which simplifies this. And then distribute that coefficient over this. So this becomes a coefficient of 32.4 times R52.3 minus X2. And again, these are just placeholders. They're not variables. We don't operate math on them. Multiply 32.4 times the resistive value, 52.3, and also multiply it by the reactive value. That gives 1695 ohms minus X 64.8. So that's 1695 resistive and 64.8 capacitive. Houston, we have a problem. Because at this node, that's the impedance looking back this way. That doesn't jive with that circuit because that implies that this needs to be inductive to offset that minus 64.8 ohms. There's a reason that's the way it is, and I'll explain that shortly. The reason for that is that I'm doing some what-ifs from Radio Engineer's Handbook using the formulas as a quick and dirty way to calculate these values. But I'm getting real close to a case of 180 degrees phase shift where these values come real close to resonant and they get a little flaky. With a little bit of error, they can just suddenly flip sign. And that's what happens when you get an R value minus X2 ohms. That's so close to resonance, you may as well call it resonant. And there's really no practical way to build a circuit like that with 2 ohms. There needs to be a bit of a difference. But what I'm doing here, and the answer to why it's worth doing this math instead of just doing the formulas in Radio Engineer's Handbook to directly calculate these 3 values, because we can't just take assumptions or givens of input resistance and output resistance and calculate these, because they're 3 unknowns. And the process that Terman shows part of to find these values is assign an impedance to each of these component values and use simultaneous linear equations and linear algebra to derive equations for these. It's too messy. He didn't put it in the book, but that's what it is. But this lets me do a proof as to whether the values I've come up with are accurate, and in this case they're wrong, and this circuit will not work. But it's an assumption, because I wanted to begin with the assumption of a blocking capacitor here as part of the pi network without a separate blocking capacitor here and a shunt inductor. So I wanted this T form exactly. For the assumptions I'm using of 1700 ohms plate resistance and 50 ohms out, that might not be possible. While the formulas for the impedance of each of these in Terman's Radio Engineer's Handbook is exact and easy to do, it only gives the reactances. And for certain frequencies, then we find the component values from simple formulas. The problem is that tells us nothing about selecting these components, because, especially with this being a high voltage, this is 2 kV here, 2 kV DC and possibly 2 kV RF, peak to peak. These components are under high voltage, and we got to know the values of these to make estimates or calculations of the voltages. We know the voltage here, know the voltage here because of the transform ratio. We've got to know the voltage here to be able to find the voltage across each of the components, and therefore not only rate them as their inductance or capacitance, but their voltage and current ratings. And it's especially a problem for capacitors, because capacitors are rated at DC plus AC voltage, not either or. So that must be a high voltage capacitor there. Something like 2 kV there, something like a few hundred volts there. So this can be a much lower voltage rated capacitor. The inductor isn't quite so much voltage rated by itself, but that's the rating of the insulation, and I'm going to use toroids, so a rating of the toroid core on which that's wound. And that is that. But I'm trying an old trick with this amplifier. C sub P with this big power grid vacuum tube is rather high. It's something like 11 puff. And at 6 meters, that's a huge amount of capacitance. That's most of the value that would be of a input capacitor to a pi network, just in straight capacitance between a tube and a shield. So what I've done is take that as a parallel network in admittance. 2500 ohm plate resistance, I think it was 11 puff here, and used a transform like this up here to transform that to a series equivalence, and something neat happens. there's a significant transform down in resistance for nothing. No components. Went from 2500 to 1700 ohms with an imaginary capacitor in series. And I mentioned in a previous video, capacitors, real capacitors block DC. This one will pass it. Not a literal capacitance, but it appears to be capacitive reactance. So that's the plate terminal. That's the plate terminal on the tube with the shield. But the shield capacitance is now reckoned to be in series, and that can be tuned out with a series inductor to make a purely resistive node up here looking out to the output network. So there is why it's not good enough just to go grab a formula. We have to understand the circuit, about the components, and about the math. And it's just throwing together a circuit from some formulas in a handbook is not necessarily engineering. This is. And this is not new. A broadcast engineer told me that this has been done years ago in commercial transmitters using the shields for tuning. So there's a calculation. It's a bit convoluted. Just remember the magic formula. Take the impedance R plus or minus X, flip the sign to the numerator, square these two, add them together in a denominator. Very, very simple. Okay, BYP out.